Welcome back, everyone. This is our last part for module 2. Today we are going to take examples and talk about basically the multiple cycle instruction computer. And we stopped last time when we talked about the encoding of the data path signals. These are the signals that we are used to. This is the extra part for temporary registers. Here we have the encoding for the next state, which we said we can have 16 states. And here is our program counter. It's 00 for PC hold, program counter select, sorry. We have 01 for increment, 10 for branch, 11 for jump, and you can see here instruction load is either 0 or 1 depending on the complexity of the instruction. So we need to create a state machine diagram, or what for short we call it an SMD diagram for a multiple cycle computer. So an SMD diagram is based on the sequential operations of digital systems, which we studied in level number 2. So an instruction requires two steps: the instruction fetch and the instruction execute. So most of its instructions will be requiring two cycles at least, because the instruction fetch is done from a memory and we may need the memory again, so we need two cycles. So this is our first part, which is the specifies these instructions, which are move A, increment, add, subtract, decrement, or exclusive, or not. Now these are the cycles. The first cycle we do instruction fetch, or the first clock cycle we do instruction fetch. In the second clock cycle we do execute. So the execute, the first one is move, this one is increment, addition, this one is subtraction, okay, and so on. We do all the instructions as you can see over here. Then once we finish, we do the increment of the program counter, and then we go back to the instruction fetch. The second part will include the move B, shift right, shift left, load immediate, add immediate, load store, branch on 0, branch on negative, and jump. And this is shown basically over here. It's the same idea. The only differences are, or may happen, somewhere around here, where we have the jump instruction, the branch instruction, with options of changing the values of the program counter. With the options of changing the values of the program counter, all normal instructions will go to the value of PC plus 1. However, if you have a branch instruction, then you are going to change the value of the sign extended value, and you are going to branch to these new values and go to instruction fetch. Okay, so let's take an example. Before the example, this is the state table for all of these instructions. This is just to simplify or to sum up all of these instructions. So for example, let's take this example, which is the shift right and shift left instruction. Our starting point is the instruction fetch over here. Now once we fetch the instruction, we get that the instruction has the opcode of this value, which is 0001101. So 0001101, which is the shift left instruction, and shift right instruction. Okay, shift left, I cannot see it here, I will go here. Okay, shift left instruction and shift right instructions. So if once I fetch my instruction, I find this instruction or this instruction, which is this is shift left and this is shift right. Once I find them, immediately I will move RSA into R8. I will move RSA into R8. Now once I move RSA into R8, I'm going to check the Z flag. Okay, now because this instruction is a little bit different, we are going to check the value of or we are going to shift multiple times. The number of times we are going to shift is stored in RSA. So let's say I'm going to shift left R5, sorry, or shift right R5 3 times. So this number 3 will be stored into RSA in the instruction. Okay, now if RSA is equal to 0, this means I don't need to do any shifting. Okay, this means I don't have to do any shifting. So first of all, we need to check is if the value we are going to shift is equal to 0 or not. If it's equal to 0, then we go to instruction fetch and stop everything. There is no need to do anything in our instruction. Now, if this is not equal to 0, then we are going to have this value, okay? Meaning it's not equal to 0, so z complement will not equal to 0. So we are going if it's equal to 0, then z is equal to 1. If it's not equal to 0, then z is equal to 0. And because this is the z flag, so this one will equal to 1. Z complement will equal to 1. So we are going to the first execute part. In the first execute part, we are going to move the operand with 0 fill into R9. The operand will hold how many times we are going to shift right or shift left. Now, if the operand is equal to 0, then instruction fetch, stop. There's no need to shift right or shift left. So the first one over here, basically, again once more, if I want to shift right R5 and put the result into R4 3 times, so the 3 times is my operand and this is my RSA, okay? So this is my RSA. So RSA I here, first of all, I will going to check is RSA equal to 0? If yes, no need to do anything. If no, check is the Z flag equal to 0? If yes, exit. If no, go to execution number 2. In execution number 2, we are going to shift right R8 because we shifted RSA into R8, and then decrement R9 because it contains our operand. Now, if R9 is equal to 0, move the result into where we want to store it. If not, go back to execution number 2 and keep repeating this cycle until R9 is equal to 0. Finally, over here, we are going to store our result R8 into RDR. Here it's equal to R4 in our example, and then we are going to exit the file. This is the execution table for this shift right and shift left functions. And in the tutorial, we are going to have more functions, and you are going to try to do more functions on the state machine diagram. So this is all for module 2, and hope to see you all soon. Thank you for watching, and thanks.